It's nice to be here, and it's nice to have a couple of brave souls who want to sit in the middle here. I see that most of you are on the sides, but I can deal with that. As explained, I have job titles, but my actual job description is Hannes does whatever he wants. But even on a day like today, I have some stuff that I have to do. I have to do the technical talk in order to be able to do the fun gig tonight. So, what's on the agenda for today? I'm first going to explain a little bit what I was building as a sample application for this talk. Then I'll dive into the general design ideas that I wanted to achieve and why I wanted to use AK.net to actually build this. And then we'll dive into some implementation details. And before you know it, the 45 minutes are going to be over. So, what were we building? We were building beersender.net. And why was I building beersender.net? In the pandemic last year, I was really bummed out. Like, for the third or the fourth time, Belgium went on lockdown. I took it really hard, and I figured I want to do something fun. So I had an idea. I live in Belgium, and what is Belgium known for? Beer, exactly. So I figured if I take beers and I put them into a box and I send that box to my friends, everybody will be happy. That was the idea. So I set out to do the fun part, and I bought a lot of local Belgian beers that I found tasty, and I threw a couple of curveballs in there, and I put everything into boxes, so I had a very nice selection. And once the boxes were ready, I put some shipping labels on it, and my expectation was that this would happen. I would take the boxes, and I would give them to UPS, and they would arrive at my friends. That was my idea. Now, it turns out that that is not how things go. You give boxes to UPS, and whatever lives inside the Schengen region, that gets shipped nicely. Everything that goes outside, like to the UK or Norway or Switzerland, those boxes actually got returned to me. Because as it turns out, I don't have a license to ship beer, right? So it turns out that once the boxes showed up on my doorstep again, I had to recuperate my money from UPS. So what was actually happening is I was tracking packages and providing extra information for the customs office and sending a lot of unstructured emails with people who seemed like they didn't know what they were doing. I had to deal with the UPS help desk, which is a little special place of hell in and of itself. I had to get my money back, resend it, and so on and so on and so on. Not fun. So I figured I need a tracking application if I'm going to send beers. So sending beers is not so much fun. It's like selecting beers and making boxes. That part was a lot of fun. I had so much fun doing that. Like getting the boxes to where they needed to be, not so much. Now, it only took me 6 months to get all of those boxes to the 8 people that I wanted to send them to. So I started sending them in January. Last box arrived in June after a third retry. So yeah, beersender.net. Now, why do we call it beersender.net? We're not savages. We're not writing in a VB6, so we're calling it .net. Please stop doing that. Stop calling your applications .net because they were written in .net. Nobody cares what programming language you used, okay? So, when I was thinking about this application, I was thinking about the stuff that we would need to build this and what design ideas I wanted to put into the software design. And for me, my DDD journey started by trying to read this book. I got all the way through to chapter 7 and then parked to the side, and then I read the Red Book by Von Vernon first and then returned to this book. I mean, the whole this thing goes. But what DDD is about is mainly you're going to try to model your software to reflect your business case as much as you can. And on a high level, that means that you are going to try to make one ubiquitous language together with your business people so that when you're talking about a certain concept, it has the same name in the business as it has in the code. And if you look on a high level on a systems design, all your services are going to be bounded context. And a bounded context is a place where your ubiquitous language is valid. If you're using that language, it holds true in this certain service in your software. Because a customer might mean something else to your billing department than it might mean to your shipping department, and then it might mean to your customer relations and whatever. So it's very important to define the boundaries. And on a low level, we're going to want code that expresses our domain really well so that we have a place to reason about what's going on. And if you're thinking in DDD concepts, one of the places where you're going to start reasoning about what is going on is an aggregate. An aggregate is a concept for a place where you can reason about a certain command or event being processed. Something is going on, and your system is going to respond to it. Now, it's very often that you see these concepts, because this book was written from an object-oriented perspective, and you see it nowadays, you see the DDD concepts more often than not. You see them applied with CQRS and event sourcing. So what does that look like? And there's two things that you have to know before we dive into what I'm going to show you today. I'm like taking a book and putting it into 3 minutes, right? You have to know about commands. You're going to send a command to your system, and a command means it is a request to perform a certain operation. You're going to request that the system does something, and effectively, you're issuing that command in imperative form. Send beer, for instance. And your system is going to respond. It can either respond with a success, which means that the beers have been sent, which is an event, which is in the past tense. It has taken place. We can no longer change it. Or sending of beer failed because we didn't provide shipping information or whatever, right? So those are events. So commands lead to events most of the time, and events are a truth that we can no longer change because it already happened, and a command is a request to do something. Now take that into an architecture. If you want to build software through the CQRS patterns, you're going to look at something like this. And the whole thing that CQRS stands for, it stands for Command Query Responsibility Segregation. All it stands for is that the read side of your application is separated from the write side, and you are using different models on both sides. So the software model that you use to process the commands that go in and to do your write operation, that will be separate from all the queries that are executed on your system because they will be on the read side, and they might have a different data structure. And often you see it applied where the command side and the read side are connected through events. So we have the command side where we are changing the state of our system, where we validate our command and see what events are coming from this. And then we put those events on a bus, and they are processed on the read side. And on the read side, we will use that to transform our read storage. And in an ideal world, we can make it so that every query on the query side is going to hit an index table in our read database. Optimum performance always, right? Now, we're not even talking about event sourcing here. You can still do this with very normal relational database patterns. But the DDD world is like, okay, if we're already doing this, we can also think about event sourcing, where state is considered as the result of all the events that have taken place in the past. And the example that gets often used when this is explained is a shopping cart. I'm going to put a product into my shopping cart, and I'm browsing along, and I find something better, and I put a second product in, and I take the first product out. If I only save the state of my shopping cart, I'm going to lose a lot of important business value. Because if I want to optimize my recommendation engine, I'm going to have to know that a user first put in that one product and then took it out again and put something else in, right? And that is what event sourcing is all about. We're going to save the entire event stream and look at everything that happened in the past, knowing that if we need to recalculate the current state, we can always do that. We can also recalculate state for any point in the past, which is an added benefit of this kind of architecture. So if you're looking at the command side of the previous slide, like this one, if you look at the command side, if in the command database, we're not going to be storing the actual state, but we're going to be storing all of the events. That is like the model that you see applied a lot today in the DDD community. It's like you're going to use event sourcing with a CQRS architecture to build software systems. And this has a lot of advantages. One of them is performance, but there is also an advantage that you can reapply past events to new features. So you're going to build a new feature, and you can reapply the event stream and have data that represents like everything that happened in your system in the past. And that is something that is a lot harder to do if we look at current state databases. If we only save the current state, we have to do a lot of guesswork to populate new features, and with this, that works really well. So, for my beer sender, I want all of this. I want to have CQRS with event sourcing. I want to be able to build clean aggregates. What that means, I'll come to that in a second. And because I'm not a savage, I want human-readable unit tests. So, why did I choose to use Akka.NET to do this? Now, first of all, what is Akka.NET? We had Akka on the JVM, mainly used with Scala as a programming language. And around 2015, a lot of actor models were brought to the .NET ecosystem as well, because over the course of a couple of months, we had Orleans, we had Akka.NET, we had Service Fabric, reliable actors, and so on. Now, this is an implementation of an actor model that already existed since the ideas existed since the 1970s. But the reason that we're getting this now is because we are faced with a lot of multi-core systems if we want to scale. Because single-core performance is not really increasing anymore the way that we were used to having it, but what is increasing is the number of cores. When I started my career, it was normal to have a Pentium 3 with a single core as a desktop machine. We now all have 8 cores in our pocket on our smartphone, right? So if you want to do multi-threaded stuff, we're going to need a programming model that deals with this, and this is where the popularity of these actor models really comes from, because they are very nicely built multi-threaded programming models. And it does that by modeling the reality of the code after the way that the physical world works. We are all persons and objects in a real world, and it all interacts with each other, and that is the way that an actor system also works. You have all these actors that are sending messages to each other. And to do that, we are using the reactive manifesto, and we're using reactive patterns that allow us to build these highly concurrent systems that are very good at doing multi-threaded stuff. And as you can see, Akka.NET last year already had more than 5 million downloads, so that's pretty cool. And they are actually maintaining this really well. It was a straight-up port from JVM Akka. It is diverting in some interesting ways at the moment, but it's a very reliable system that is actively maintained. Now, what do these actors look like? The basic building block if you build an actor system is an actor, and an actor is just an object that derives from a base class, an Akka.NET package base class. And these actors, they hold their own state. So nobody else can access your state. Your state, or like properties or fields, I mean, you're all programmers. It's not really that hard to reason about. And then it also has behavior, functions, right? So functions are the behavior, state are properties or fields, and the actor has an inbox. And the inbox is the only way that we can ever talk to an actor. If we want an actor to do something, we send it a message. And the messages are dispatched one by one in order. So we are always, is it flickering for you as well? Okay, is that something we can solve, or is that just something we're going to deal with? Okay, that's fine. I'm going to blame Lenovo. Is that okay? Can we blame Lenovo? Good. Okay. So these messages are processed one at a time. And the powerful part of that is that you are always sure that there is no other thread running on your data, because nobody else can access your fields. You're as a single thread running on your... So you don't need to do any locking. You don't have to worry about race conditions or locking calls or whatever. So writing code that is concurrency safe inside an actor system is really easy to do. Now, writing this in C# is actually really, really easy. You inherit from a base class, and this is the untyped one. You implement an onReceive method, a method for the messages to come in, and then you do something with those messages. That is it. This is the implementation of the simplest actor that we can write. And the cool thing is that we don't have to worry about the more complex stuff. Now let's first talk about messages. The messages that we're going to send to these actors, they don't really need a base class. You best design them immutable, as with any messaging system. It's always a bad idea to start tampering with messages while somebody else is processing them, especially since if you stay on the same node in an actor system, your message does not get serialized and deserialized. What you do is you just pass around the object reference, which makes it really, really fast, but it also allows you to tamper with it, so just don't do that, okay? Last tests I ran, because I have a new machine since I wrote this talk, I can process 10 million messages a second on a laptop. So if you take a beefy server, getting 50 million messages a second should be no problem. Just to give you an idea on the type of performance that you can get with this. And I know that Metallica released a new album a couple of weeks ago. Any Metallica fans in the room? Yeah. So this dates me. This is the Metallica album that I grew up with. It's still the best one out there. You can fight me on that later if you want. But your actor system is much like your puppet master. It does all the heavy lifting for us. It will create our actors. It will take down our actors if there is memory pressure. It will manage all of the inboxes. It will schedule threads to do all the processing of the messages on our actors. There's even an event bus in there that allows for pub-sub messaging between actors as well. And the cool thing is that for all of this, we don't really need to do anything except for this. We call ActorSystem.create, and we give our actor system a name, and we will have one running. But as I just told you, our actor system is going to create our actors for us. And the way that that works is with props. Props are effectively, if you would say it in, because I heard that Andrea was working in C++, if you think in C++ terms, this is a pointer to a constructor. It'll tell the actor system which constructor to use with which constructor parameters to instantiate your actors, because this takes a param array of object, so you can just pass in whatever you need, and it'll map to your constructor. Now, with those props, I can call actor off, and that will spin up an actor for me. But I'm never getting the actual object reference back. What I'm getting back is an iActorRef. And an iActorRef is a simple object that allows me to talk to the inbox of the actor. That's all it does. So I never have access to those properties. I can never meddle with maybe trying to change something while another thread is processing a message. It will never happen. All I can do is do a tell and send a message to the inbox of the actor. And that is how that works. Now, how do these actors, how are they structured? There are 3 actors that you get for free. The blue ones, they are always there. You have a root actor, a user actor, and a system actor. And underneath the system actor, that is where all the thread scheduling and event bus stuff lives. The stuff that you usually don't touch when you're building actor systems. The ones that you instantiate, the one that we created in the previous slide, those are top-level actors, and they go under the user actor. So the one that we created was one of those top-level actors. And your position in this tree defines your actor address. So the one in the bottom right is /user/a2/b3. Interesting. Now, why is this important is because, the way that that works, if you create a child, and this is the strongly typed actor, which will feel a lot more comfortable to C# developers, because you're no longer dealing with something that just gives you an instance of object and you have to figure out what type of message you're getting. You can register event handlers or message handlers for strongly typed messages coming in. And you can register as many as you want. So that makes it much more convenient for C# developers to get into this. This is the one I always use as well. But if we are creating a child, instead of doing ActorSystem.ActorRef, we can do context.ActorRef, and context.ActorRef will actually create a child for this actor that we're currently running in. So that's how this hierarchy becomes this tree that we were seeing. And why is this hierarchy important? Is because we have something called supervision. As was already mentioned, I have 3 children. If I take them to the supermarket and they misbehave, who is responsible? Me, right? Everybody who has kids knows this. If my kids misbehave, it's my fault. And it's the same with actors. If one of your child actors misbehaves, it's the parent actor's responsibility to solve that. Now, what do I mean by that? Is if a child actor throws an uncaught exception, the parent actor is actually going to be the one dealing with it. And that actor is going to be asked to take an action and to see what is going to happen to this actor. And I can either resume. Resume means, okay, it's okay that this message failed, just pick the next message. So the next one from the inbox. You can also say stop. It's like if your child, if it's really misbehaving, and you know that you will never be able to recover from this exception, what you're probably going to do is throw away the entire inbox, throw away the ActorSystem, kill the actor. Don't do that to your kids, okay? But you're going to kill the actor, and it's going to be gone. Restart means keep the inbox, throw away the actor instance, recreate it with the same props, and try and dispatch the same message again. That might solve the situation. That's a restart. And if you don't know what to do anymore, you can also escalate to your parents so that you call it up the hierarchy. And you can either apply this action to one of your children or to all of your children. Why would you want to apply it to all of your children? You might get into a situation where you have cut a huge workload into smaller pieces, and one piece failing invalidates the entire workload, then you're going to want to stop processing on all of them, right? Now, supervision is the part of ActorSystem that makes them extremely fit for self-healing scenarios and for high availability. Like ActorSystems were first brought into practice in the 1980s by Ericsson, and they managed to get 9 nines of uptime, so 99.99979%, which means 31 milliseconds of downtime a year. Who gets that on their system? Yeah, nobody, right? Me neither. But these ideas help in doing high availability stuff. Now, what does that look like? You override the supervisor strategy method on the parent actor, and that is going to get called whenever a child throws an uncaught exception. And you can return a strategy that inspects the exception and returns a certain directive to see what needs to happen to this child actor. Now, the one thing I haven't talked about is state. Until now, we've been talking about actors that live in memory, but as soon as we recreate them, we lose all the fields that are in our actor because it all just lives in RAM. Now, there is a persistence package on top of aka.net that allows you to recover in an event-sourced way. You can save snapshots, you can save events, and once the actor is recreated, what it will do is it'll pull the snapshot out of the snapshot store, then replay all the events that have taken place since the snapshot, and then it will actually be able to take in new messages and persist those again. Now, these persistent actors, they take a little bit more code, and I'm going to skip over this really quickly. There's another base class that you need to use. You always need a persistence ID, and that needs to be unique over your entire actor system, because that is going to be the key that it uses to query the storage. So that has to be unique, so I have to put some kind of ID in there. And what I always do is I group all of the state of my persistent actor into one object, so that if I have to do snapshotting, all I need to do is save the snapshot, the state object, and if I recover from a snapshot, I need to override the state object. I'm done. So that makes life a little bit easier. And now we have a difference between commands and recovers. A command is a message that's coming from the inbox. A recover is something that is coming from the persistence mechanism. We can also deal with snapshots. The recover is where the snapshot is offered to our actor on the recovery. We can also get messages because snapshots are saved out of thread, so we can get a response back like whether our snapshot was successful or not. This is how that code looks. I'm gonna skip this because it's not really relevant to the rest of our story, and we will run out of time afterwards. So the reason that I put these two stories together, DDD and Actors, because both of them try to model code after reality. And that's interesting to us, right? They're both message-driven by nature. They all think in terms of, DDD thinks in terms of commands and events, and these actors, they work with messages, but you can put commands and events in messages as well. The persistence model in Akka.NET is event-sourced by nature, and we have a publish subscribe event bus that is going to be very useful if we do these projections on our read side of our CQRS model. And as an added benefit, we get something that is pretty high throughput, and that allows us near linear scaling if you design your system correctly in a clustered way. And that is what these actor systems are really powerful at, because a lot of your code is parallelizable. It scales nearly linearly if you add resources to a cluster, which is fantastic. It's the unicorn of scaling. So, some of the basics on how that works. We know what we want from our beer sender. Let's look at how we can bring some of these things together and what you would need to do if you would build a system in this way. Now, what I'm going to show you is not production code, okay? If you're going to build a system like this in production, you're actually going to be doing a little bit more work than what I'm going to show you, but at least you will get the ideas on how the bits and pieces fit together. Right? Now, first of all, our aggregates, I wanted to design them without dependencies, so that should I switch to another architecture, I could maybe reuse them, right? And I want the aggregates to be agnostic of the storage mechanism that we're gonna use. And I wanted to have those clean unit tests. Now, if we abstract an interface very roughly of what I want my aggregates to be able to do is I want to be able to take a command and see what events are coming from processing that command. I want it to apply that event in its internal state, right? And the reason that I took the state mutation out of the check command method is because we're going to pair this with the persistence mechanism of Akka.NET, which means we can call all of the apply events when we are replaying events for a new actor that already had stuff in the database. And if we are processing a new command, we can actually just loop back the events and apply them as well. So the way that we implement these aggregates, all of our fields are just going to be properties. Very straightforward. No need to explain that any further. We are going to set those with events. So if we are, and this is where we get a command, and in a command we will check our internal state, and our internal state will give back the events that are coming from this command. And why do I use IEnumerable event? It's because then you can use the yield return keyword. It makes it very easy to return multiple events in a case that you need that. So we just check state and return events. Very easy. That's the command side. On the event side, also very easy. When we apply an event, what we're going to do is set some of those fields that we had 2 slides ago. So any apply on a certain event that we're getting is going to set the properties of our aggregate. Now, why is this a fun way of writing software? I'm going to skip on the test base class. I'm pretty sure you can figure it out if I'm going to explain the way that the tests look. If we write tests for code like this, you can write tests that your business people will even be able to read in code. Because this reads like a story. When we create a new shipment and we add a beer to the box, and we add a shipping label to it, if we try to send the beers, what we expect is that the beers have been sent. Like, take away the new keywords and the round brackets, your business people can read these tests, and they can reason about these scenarios with you. These are acceptance criteria for your software. If you can get to a point where you're writing these tests together with your product owners, you have already eliminated so much of the translation difficulties between the business and the programmers. All you need to do now is implement it so that this test becomes green. And when these tests fail, it's very easy to see why and which cases might be broken, and you can reason with your business people again. So that's the first advantage of those actors. Now we can wrap this inside one of those persisted actors in a very easy way, because if we implement that aggregate interface, what we can do is we can use the persisted actors to actually do something like this. Our persistent ID, you can have the type of aggregate that you're doing, and then the aggregate ID as a persistence key. And what you're going to do is you have events that are actually going to be coming from the recovery side, and then you're just going to apply them to the state. But you're also going to have events that might be coming from the inbox, in which case you're going to persist them first and then apply them. Commands are also going to come in through the handle command method. Now, when we get our snapshot, all we need to do is replace our internal aggregate, because we've serialized all of the properties of our aggregate and put that into our snapshot store. So when this actor spins up and it queries the snapshot store, we just replace our aggregate and we're good to go. Then we're going to reapply the events that have taken place since the snapshot. And with the apply event method, we can keep a counter, and every 100 events or so snapshot our aggregate if we want. We have full control over snapshotting in Akka.net. You can do it time-based, you can do it every so many messages. You can, whenever you call save snapshot, the snapshot is saved. Now those are the important things, but if we now get a command, and this is the powerful part, we're actually going to check what events are going to come from that command, and then we're going to persist the events. We're not persisting the command, we're persisting the events. The event stream is what we care about in an event source system. So we're going to persist all of the events and apply them to our aggregate right away. That makes sure that when this aggregate stays in memory, because that is how Akka.net works, these actors stay in memory until the system disposes them or until you send a poison pill, for instance, to an actor that spins it down. But at least they stay in memory. So for subsequent commands, this is extremely fast. You don't need to rehydrate your aggregate. No, it's already there. It's living in memory. It's waiting for the next command. And in most software systems, you have your hot aggregates. Think about like our beer sender, whatever packages I am shipping today, those are the ones that all the commands and events are going to happen on. All the ones that were shipped last year, they will probably not be in memory anymore. But the ones that are in memory, I can respond to those requests really quickly. And if you build that generic actor, making one for a beer shipment is really easy. You just implement the generic base class and you're done. Now, how do we piece all of that into an actor hierarchy for all these things to work? Now, in our user space, the first thing we need to look at is all of our aggregate actors. And for that, we are going to create an aggregate manager. The aggregate manager has only one responsibility, that is creating a new aggregate actor whenever we need one for a certain aggregate ID. It means that it's not already there, we're going to create it. That's it. But then we need to relay all of our commands to it. And for that, that was the explanation of the aggregate manager. So what it's going to do is, if you have a sender that sends a command, it's just going to check, okay, good, I don't have an aggregate for that yet. Create one, and it sends back the actor ref. Do I have time to explain something cool? Okay, no, I do. Actor refs have something called location transparency. And location transparency means basically that in a cluster or a remoting scenario, this object can be serialized and deserialized, and it'll still work. Which means that if you pass around an actor ref throughout your cluster, you don't have to know where the original actor lives, on which node. It'll just work. If you do actorref.send or .tell, you will actually send a message to that actor. So the aggregate manager just does that. If you send a connect for a certain aggregate, it'll create the actor and send the actor ref back, and it doesn't really matter which node it goes to, it'll work. Now the command router, that is the tricky part, and I'll come back to that in a couple of slides. That is going to take in all of the commands on your command side of your CQRS system. All the requests to perform operations. And your command router is going to be aware of which aggregate actors are already in memory. It will have actor refs for them, and it will relay the commands to those actors. If it doesn't know about a certain aggregate, it will send a request to the aggregate manager to create it. But this may become a bottleneck, and bottlenecks are a real thing in ActorSystems. Because there is always only one thread running on a single actor. If you send more messages to an actor than a single core or a single thread on your machine can process, you will actually hit a point where your inbox will overflow because your actor cannot keep up. There's ways to solve that. I'll get back to that if we have time in a few slides. And then your projectors on the read side. Your aggregates are actually going to be publishing events on the event bus. You may have noticed a few slides ago that there was an event stream.publish. I'll get back to that, how that works in a second. But they subscribe to those messages, and what they will basically do is insert, update, delete data into our read store. That's it. I'm going to subscribe to events and use that to mutate the read stores. And on top of that read storage, I can then build my read API on my secure system. We also get ways to integrate our system. We often have to make calls to external software systems or subscribe to stuff that is coming in. I call those subscribers. They can relay messages between aggregates. They can relay messages to outside of our system. They can subscribe to stuff that is happening outside and relay it back to the inside. So that's our integration model. And for every way that we want to integrate, we're going to have an actor that's living there and that publishes stuff on the event bus. Now, how does that event bus work? Every actor has a bunch of properties that are set before a message is being processed. For instance, the parent actor, the sender of the message is set, so you can reply to the sender if you want. But there is also a context, and on the context, you can access the system where you have the event stream. And all you're going to do is publish your message on the event stream. You can also do it from the outside if you want. If you have access to the actor system, you can also publish to the event stream from there. Now, the only filters that we have on the event stream are based on the type of message. So for your projectors, it's really important that you think in which types of messages you make, because that's the only way you can filter on things. So you sometimes are doing message inheritance, just to make sure that you can filter on the right messages. Now, your command router, as I said, might become a bottleneck. And Aggregate also has ways to solve that. And this only works with stateless actors, right? You can basically make a group of actors that are going to process a single inbox. And you can use different routing strategies. For instance, you can do consistent hashing, where you compute a hash based on the contents of the message and decide which routee it goes to. You can do round robin, or you can do smallest inbox or whatever. There's a whole bunch of distribution mechanisms for routers. But this assures that there is an inbox in your system that you can process in multiple threads, which solves your problem where you run into the point where a single thread cannot keep up with an inbox. And creating a router is actually not that hard. You can see it on the right. The routers are put into the props. You can also configure them from the outside of the ActorSystem. But doing a router, in this case, we're creating 5 actors that are going to round robin on that single inbox. So if you have these bottleneck actors, this is the solution that Aggregate.net proposes to that. And I have 5 minutes left? Ooh, 2 minutes left, okay. That's good, time to wrap up. In short, we put our aggregates in actors, we put our projectors in actors, we're gonna model our commands as messages, we're gonna model our events as messages, and our event sourcing is actually already built in. So building this is very, very low friction. I'm trying to say is like, if you try to use an actor model and Aggregate.net specifically to build a DDD-like system, you will encounter very little friction because all of it maps really, really well together. Now, there's so much stuff that we have not talked about in this talk. For instance, you're going to want to publish events back to your UI because often when you're building these systems, you will have a command endpoint that you're going to send all your commands to, but you're going to want your UI to update based on the events so that you create an event loop between your UI and your backend. So you're going to need WebSockets or SignalR or whatever to make that happen. You need to configure ActorSystems, especially for clustering. We used to only be able to do that with HOCON. Now, what is HOCON? It stands for Human Optimized Configuration Object Notation. That's a mouthful. Just to say, like, it's another configuration file format. It looks almost like JSON, but it's not JSON, so it's exactly what we needed. This is something that came from JVM and that was ported. Now, there's good news. Since Aggregate.net 1.5, we can also configure it in a way that you are used to configuring ASP.NET applications with a builder pattern, which is so much better. You're going to have to inject some logging into this. There is a paid module called Phobos. Now, what that does, that is the only paid component in the entire Aggregate.net ecosystem. It's built by the people who build and maintain Aggregate.net. Now, the cool thing about Phobos is it's basically your telemetry data on your ActorSystem. It allows you to monitor inbox sizes, response times, everything, number of actors, all of those metrics. And it's completely open telemetry compatible since version 2. So that is pretty cool. If you want to have visibility on your ActorSystem, I suggest that you pay for this. There's no way that you're going to write it yourself for that amount of money. And if you want to start learning, there's a free bootcamp on, I'm not affiliated with BetterBridge in any way, by the way. I just like their stuff. But there's a free bootcamp on GitHub. There is a fantastic blog where they blog about all the new features they release. The contents of it are really, really high quality. It is the first software product where I find better info on the site of the builders than I find on Stack Overflow, and that's saying something. They also offer remote paid training, which is really worth it if you're a team that really wants to get into Aggregate.net. I think that's most of what I wanted to tell you. I could talk about this for a few more hours, and I will if you come talk to me after this. My name is Hannes. I'm the head of learning and development. That means Hannes does whatever he wants at Access in Belgium. That is my Twitter handle and my ICQ number. I'm on a mission to make ICQ great again. And since last year, I can call myself an MVP, which I'm really proud of. Stay tonight at 7. We're going to convert that set list on that stage. Like, take a bunch of nerds and ruin some of your favorite songs, probably. But it'll be fun, we promise. So stick around for that. It's going to be great. I'll be playing a guitar I built myself. So if you're a guitar nerd, please also come talk to me after this.